Okay. All right. How are we doing? Doing okay, everyone? Yeah. Okay. So let's start. Let's get back into the partial derivatives and tangent plane ideas, and just kind of, this stuff is not too bad. We've kind of sort of seen how it works already with the tangent planes and everything, but I want to talk about something called a differential, and I want to start getting towards directional derivatives. But let me just remind you. So partial derivatives, we sort of defined last time. So say let's actually do a function of 4 variables. So we have 3 partial derivatives, right? We have f sub x, f sub y, and f sub z, which we could write as dw dx with this curly d, or df dx like this, dw dy, or df dy. They're all different notations for the same thing. Right, all 3 of these things on each line. And this is the idea is you pretend here now we'd have 3 variables. I'll do an example in a second, but you pretend y and z are constants and differentiate with respect to x, right? Pretend y and z constant and differentiate with respect to x. And I use WRT for with respect to. Okay. And then basically these other ones are the same thing, right? It's pretend x and z are constants for the partial y. And then differentiate the y variable. And this one is pretend x and y are constants. Can I do one of these things? But differentiate respect to z. Okay. Yeah. So let's do an example. Let's make it a little bit tricky. See if we remember how to differentiate. This is some function of x, y, and z. Actually, let me do something like a plus 4x, just to keep some like things in mind. Okay, so let's all take a minute. Well, maybe let's do the f sub x together, and then maybe I'll give you guys a few minutes to try to do the partial y and the partial z. Right? So partial x. So let's look at the first term. I have sine of x times a constant. So sine of constant times x. You guys remember how to differentiate sine of a constant times x? Like, what's the derivative of sine of 5x? Somebody's saying it. I can't tell you. 5 cosine 5x. You guys remember this? It's like the sine becomes a cosine, and it's a chain rule, right? You differentiate the sine, that turns into a cosine, and then you differentiate the 5x, and that pops out a factor of 5. So sine 5x becomes cosine 5x, but you have to differentiate the inside. Familiar? Okay, so what does that mean here? We get y cosine xy. Y cosine xy plus So we're just treating y and z as constants, right? So this, we were doing some of this last time. This whole thing becomes constant, so it just sits there. So the x squared just becomes 2x. So it's plus 2x yz cubed. E to the xz is kind of similar to sine of xy, right? Right, it's e to constant times x. So what's the, or sorry, I had e to the 5x. What do you get? Someone say it. Yeah. Well, if I'm differentiating with respect to x. Yeah, it's a good, yeah. Yeah, it's 5e to the 5x, right? Right, if it was differentiated with respect to y, like when you do the y derivative of this term, that's a good point, it'll go away, right? Because there's no y in it. So plus, so there's gonna be plus z e to the xz plus 4, right? So you just, it's just that kind of in your head, just treat the other variables as constants, the ones you're not differentiating. And I always like to, if I'm not sure, just plug in some numbers for those other variables and try to differentiate that way. Okay, so you guys do f sub y and f sub z for a couple minutes. Turn to your neighbors and chat. Compare answers. See if you get the same thing. We need to go full group work for this, but take a minute. Actually, I think about being mean and changing this just a tiny bit. If I had put a z here, it's only going to change the partial z derivative, really. But then this would have been like a 5 here, which would have been like a 25. So this would have become z squared. That would just multiply by a z. So I'm going to put that there just to make the partial z a little harder for you guys. It's fine, we're just doing this to practice. Over here and be annoying, hover over. Still using notebooks, huh? Email, yes. It's fine. I've been, like, I had this huge deadline yesterday that I was a complete crazy person about. But yeah, we'll talk. Cool. Yeah, we'll figure it out. You said we got 1 month, right? You still got some time. Yeah, good. Yeah, check with your neighbors, see if you're getting the same thing. Partial y. Make friends, people. Say hi to each other. We all need friends. People are, so f sub y is not too bad, right? I think people agree on that one. What did someone get for f sub y? Yeah. Wait, sorry, what did you say here? Oh, plus x squared z cubed, sorry, couldn't hear you, yeah. Yeah, the rest goes away, right? There's no y's in any of it, that's good. So that all goes away. Good. What about, should I give you another minute or so for partial z? Or are you guys getting it? One more minute? Okay, good, thank you. That's all I'm looking for, feedback. Guys, remember what to do with this? All right, plus 0, just to make that clear. I'll do the first part of the partial z. All right, what happens to this term? Someone? Yeah. That's right, the z cubed just becomes a 3z squared, right? Okay, now, who tackled this? Who feels good about this? No one? I got some head shakes. What do you do when you see this? Product rule, right? It's a product rule. How do we do product rule? First times derivative of the second plus second times derivative of the first. So what do you get when you do first times the derivative of the second? Z times the z derivative of e to the xz. What's that? Xe to the xz. So we could write this as xz e to the xz plus second times derivative of the first, and the derivative of z is just 1. So we get plus e to the xz plus 0. So that's the product rule. Any questions about that? You guys, does that sound vaguely familiar? You remember the product rule. You just probably not have used it in a while. I don't know if you use it in your personal life. Okay. So yeah, it's just that's the z times the derivative of e to the xz is that x e to the xz plus the second times the derivative of the first, and the z just becomes a 1. I could put a 1 right here if you want. I could even write, maybe I should just write z times x e to the xz like that, plus 1 times e to the xz. Make sense? Okay, good. Yeah, so I think like section 14.2 is just like practicing some of this stuff, so I'll assign some of that. Sometimes you see different notations, like I like this notation for taking the derivative. It's almost like an instruction, like do the derivative of d over dx means take the derivative of this. So you'll see stuff like d over dy, dy with the partials of an expression. It just means take the partial y derivative. So there's just, I think it just has a bunch of different notations for derivatives. We could, it's worth mentioning, like you can plug in, maybe I should just mention, again, some notational things. We can think, like that's kind of the general f sub x, like you would write an f prime, but we could plug in numbers, right? Like if I wanted to do like 1, 0, 1 or something like that. Right, we can just literally plug in all the numbers. So I think we get 0 times cosine of 1 times 0 plus, should I pick something that's going to be all? No. 2 times 1 times 0 times 1 cubed plus 1 squared times e to the 1 times 1 plus 4. So like, you know, that's 0, that's e. So you can plug in specific numbers, you know, specific points to get specific derivatives, right? Sometimes you'll also see this written as something like dw dx at like 101. That's another notation you'll see. It's kind of like maybe you've seen like dy dx at x equals 4 or something like that. That's sometimes a notation for like a derivative evaluated at a point. So stuff I'm writing here getting on the recording. Oh, kind of. Not really. Sorry, I thought I was getting more. Okay. Sorry about that. Okay, right. This is just a notation. Sometimes it says plug in x equals 4. So this is the same thing. Yeah. Okay. So you'll see some different notations. Yeah, now the other thing I want to say is there's some qualitative things. So that's kind of algebra of partial derivatives, but if you want to think about, like I think this is an example in the book where it asks you to find the sign, like whether the partial derivatives at each of these points are positive or negative, right? So, oh, sorry, let me share screen. Yeah, so like you look at this point P and you ask, is the partial x derivative positive? Is the partial y derivative positive? What does the partial x derivative mean? It means pretend y is constant, right? So if I'm pretending y is constant, what am I really doing in the, or if I'm taking y constant, what am I really doing in the contour map? Yeah, say it. Yeah, you're traveling like left and right, not up and down, right? And so really you want the derivative. It's like, what's the rate of change in starting at this point and going in this direction? That's the partial x. Does that make sense? But the partial I, you would start at this point and go in this direction. So is the partial x positive or negative? Is the function increasing or decreasing if you go this way? We increase, is it increasing? What about the partial y? Also increasing? What if we go to s? What's the, if I go this way from this point, is the function increasing or decreasing? I see it's very mumbly. I can't. You guys have strong opinions, or are you just kind of guessing? Like this contour is the 15 contour, and this next contour looks like it's the 14 contour. So if I leave the direction of the 15 contour, if I leave the 15 contour in the direction of the 14 contour, it's decreasing, right? So the partial x is negative at that point. Here, the partial y, though, is still positive. I guess it gives you sort of all 4 possibilities, right? Here at q, partial x is, you guys see these numbers. These numbers are increasing as you go away from the origin. So just yell it loud and proud. It's the partial x from this point. Positive or negative? Positive. If going, what's the partial y? Negative. Okay, good. What's the partial x here? Negative. Partial y. Negative. Yeah. So yeah, you're going towards lower contours when you leave in the positive x direction from here. You're going towards lower contours when you leave in the positive y direction from here. So yeah, so you can read the sign of a partial derivative often off of a contour map. I will say there's weird things, like if you're at this point right here and you go to the right, it's a little bit tempting to say, well, I'm probably leaving the 12 contour and going towards the 13 contour. But imagine zooming way in, because this is supposed to be an instantaneous rate of change. If you zoom in by a factor of like 1,000,000 on this, what are you going to actually see? What's this contour going to look like? a line, but what kind of line? Horizontal, right? It's a horizontal line. So if I zoom in on this point, you guys see the mouse cursor? If I zoom in on this point, really, really, really far, it's going to get, the circle's going to get bigger and bigger, and it's eventually going to look like a line, look like a horizontal line. And so actually the partial x at this point is 0. Does that make sense? So like, because you're going tangent, I heard someone say tangent. Yeah, if you're leaving tangent to a contour, partial x is 0. If the contour is horizontal, kind of at that point. And then going in the positive y direction, it's still negative. You know, you're still going down. So maybe it's worth like just drawing some of this on the board, just to like give some examples. You can read the sign or even estimate partial derivatives. I'll talk about estimating them in a second from a contour map. So just for example, stop the share. Always do that. Okay. So yeah, maybe it's worth even drawing something a little bit different, like if I have contours like imagine something like this, right? Contours. Let me label them. Let's say this is height 5, 6, 7, 8, 9, like that. And then this is also maybe 7. Well, that's sort of interesting. Actually, I think I drew something slightly interesting. Okay, so, we were just saying, if you pick a point like here, and I call this P, this is an X and Y situation. Can you guys see this picture? I call this point P. This to be a closed loop right there. Okay. Then what's the partial X at P? What's the sign? Leave this way. You just think of little tiny arrows coming out of here, right? So when we leave this way, we leave the 6 contour and we're headed towards the 7 contour. So that's positive. Leave 6 contour. And I wouldn't even say, I almost wouldn't even say like heading towards the 7 contour, because like the point is anything in this region right here, anything in this sort of, like anything in this region is between 6 and 7, right? The heights between 6 and 7. You guys agree with that? And so if I just move over to a point nearby, it's going to be a number bigger than 6. The height's going to be a number bigger than 6, right? So you're definitely increasing instantaneously, like instantaneously, you're increasing. So leave 6 contour in positive X direction. Then you're between 6 and 7, between z equals 6 and z equals 7. So that's why it's positive. Because you go from z equals 6 to something between 6 and 7. And similarly, f sub y of p is negative, right? Because you're now between the 5 and 6 contour. I guess I was going to say something like this might be a little bit more interesting. But if you use the same logic, right? Notice those partial derivatives are the same sign. It's funny, you can kind of see like because the contour goes between the 2 directions, they're opposite signs. Does that make sense? Like, because they're kind of on opposite sides of the contour, these little arrows. These are on the same side of the contour. But what does this argument say? What's the sign of the partial x or the partial y at this point Q? They're both negative, yeah? Because like we said, if we leave this contour like, and we're right next to it's the height's like 6.9 or something now, instead of, because it's between the 6 and 7 contour. It's kind of weird because this is a 7 contour and that's a 7 contour, so it's like, it seems like it could be unclear what's happening. But I think if you agree that like everything I sort of shaded in here is height between 6 and 7. I mean, we're sort of assuming that this picture is the whole picture, that this doesn't like actually go up and then down, you know? I mean, there are some assumptions you're making here, like that this is the entire 7 contour and that this is the entire 6 contour, at least in this area. Because if it went up and then down, there would be more 7 contour in here somewhere. You know what I mean? So I'll just say that the partial x of q is less than 0 and the partial y at q is less than 0. Both leave the 7 contour and go into the space between the 6 and 7 contour. Sorry, I'm just, I mean, maybe I'm belaboring a point here, but I feel like I give questions about this on tests a lot, and students often, like, if I give them a point like this, they start thinking weird thoughts. So just kind of, you just have to try to interpret this picture correctly, right? And then if I make, let me just give one more point. So if I pick the point, like a point like right here, is that a good point? Yeah, like if I pick this point for R, then the partial x, what's the partial x in that direction? Looks positive, but again, think about zooming way in. It's horizontal, right? The 8 contour would turn into a horizontal line if you zoom way in. This little arrow is tangent to this. So actually the partial x at this point is 0. So the partial x at R is 0 for the reasons we're saying. But you could say because the x direction is tangent to the contour. Can anybody see a point where the partial y would be 0? Yeah. Oh yeah, down here somewhere. Like maybe here or here. It's a little bit tilted at that point. But is that a point? Or that? Yeah, so these points, I think the partial y, or the partial y is 0. I'm running out of space here, but in your notes, hopefully. The partial y at s is 0. The same kind of reasons. Okay, so that's the thing. That's one of the things, is just trying to read these contour maps. Oh my God, maybe I should zoom in really quickly before, just on the
last like, mirror at the bottom. How is that like the 0 where if you think about it, 1x will.
Wait, sorry, which point?
Well, we don't have one on this one. So like if you were to do the bottom of the circle where you have axis,
Like there?
that would be partial x is 0, even though you're on it, you tangent, even though being in space is a little bit greater.
Yeah, but it's because if we zoomed in far enough, we'd just be following the contour. Yeah, that's a good question. I didn't say it that way. That like, if you think about zooming in far enough, you're basically following the contour, so you're not changing your height. Again, it's instantaneous. You're right. Any sort of average rate of change, you're right, would be, if I actually picked 2 separate points, then leaving the 6 contour going towards the 7 contour would be, oh, my hand's on the screen. Okay, it would be positive. It would be a positive rate of change, right? But if you think about it, sorry, I just wanted to zoom in case anybody wants to watch the recording later and actually see what's going on. Oh, wow, those are green. They don't look green. The labels of the points are green, aren't they? They don't look green on the screen. Anyway, well, they look more green that way. Okay. Sorry. Actually, it's a good question though, because it's like, I mean, if you think about it, think about the like single variable calculus picture, right? Like, let's do it right here. If you're on a curve, and now I'm just talking about like y equals f of x, right? And you're at this point, the derivative is 0, right? But if you actually computed an average rate of change and picked 2 points, the derivative is negative. So it's only in the limit that the slope becomes 0. And so there's a similar thing going on here. It's really talking like if you're looking at this bottom point of this circle, which is a good example, it's only when you like really you're in the 2 points, you know, that instead of doing an average rate of change, it's like it's only when you zoom in the limit that it's actually 0, that the derivative is actually 0. Good. Good. Okay. And then I guess another thing I wanted to say was this is kind of, I mean, this is from section 14.1, but if you you could also estimate, I mean, this is like already the contours are straight lines. I mean, that's the thing to think about. If you zoom way in on a contour map, the contours will become straight lines, right? If I zoom way in, I would have a bunch of like parallel contours, you know. Like if I zoom in here, it would look like, if I zoom in far enough, it would look like just a bunch of straight lines. I mean, this box should be even tinier, really. Like the contour maps sort of straighten out when you zoom in, just like the graph of a function straightens out when you zoom in. So that's another way to think about this, that if they all become straight lines and you can sort of tell what the partials are, it's either following a contour or it's leaving one, going towards a higher one or a lower one. Like this would be like 9, and this would be like 8.99, and this would be like 8.98. This would be like 9.01, right? That's what I'm sort of saying. If you zoom way in. Okay, so imagine that's kind of like we're in that situation here. This is just an example they gave. It's more like a linear function, honestly, but if you zoomed in enough on a contour map, you would see something like this. And then you could estimate, you could actually estimate partials from a picture like this, right? Like think about if I left like, I don't know, the point 2, 1. Like think about how you would estimate the partial x and partial y derivatives. You sort of done this already in the linear function section, but think about that for a minute while I'm erasing this board. Like how would you estimate the partial x at that point? Can anybody tell me what they think the partial x derivative is at this point? You think it's 2? People agree with that? Wait, is it Lucy? Is there any? Lucy, you were nodding. Oh, you mean you went over to the space here, from here to here is 2? Okay, so that, yeah. Oh, like these lines? Right, so that's slope 1/2. But this is x and y, and this is a function. Remember, these are z values, right? So maybe one thing I should write down, and maybe, you know, I may not have written this before, so maybe I should be careful here, that like dz dx is the limit as delta x goes to 0 of delta z over delta x, right? That's kind of the whole point of that notation. And when you think about derivatives and stuff. So I'm just asking, what's the, it's really like a slope, right? Like, how did you get to?
I went over what I did.
So you started here and you went over to here.
Yeah, that was like
Right. Or you could go from here to here, and you know this height's 14. Right. So the change in z is 4, and the change in x is 2. Right. So in this picture, in this figure 14.8 picture, doesn't really matter what point we start at because it's kind of all the same, but I guess figure 14.8, I guess that's redundant to call it a picture, it's already a figure. In figure 14.8, if we leave 2, 1 in the positive x direction, let's see, we start on the z equals 10 contour. And then at 4, 1, we land on the z equals 14 contour, right? But yeah, I mean, it's fair to say, right? I mean, I guess this is supposed to be an instantaneous rate of change, and now we've moved over 2 whole units, which seems like a ton compared to instantaneous. But so yeah, I see what you're saying. Like maybe let's just pretend we think that z equals 12 contour, we go through there. But here, since they're all straight lines, it's kind of nice, right? And so, in other words, delta x equals 4 minus 2 equals 2, and delta z equals 14 minus 10 equals 4. So delta z over delta x is 4 over 2, which is 2. And so that means, as an estimate, yeah, I mean, we could estimate the partial, right? So the partial x at 2, 1 is probably it's probably exactly equal to 2, but maybe I would just say it's about 2 here. Maybe it's funky in between. Maybe the lines aren't quite straight in between or something. There's some funkiness, but does that make sense? So now do the partial y. What's the partial y here? What do you get if you do delta z over delta y now? We leave this point, the delta y is 1, but what's the delta z? -4, yeah, -4, right? Yeah, so the delta z changes from the 10 down to the 6 contour, and the delta y is just 1. So that's -4. Does that make sense? Yeah. Contour maps always take some interpretation. You just got to sort of get used to them. But right. I mean, maybe I should just write 6 minus 10 over 2 minus 1. I guess is what we're going from y equals 2, y equals 1 to y equals 2. Okay, so that's a negative, right? That's a negative. It should make sense if you leave this point and go to, if you leave this point and go north, that the partial should be the partial y should be negative, right? Because you're going from a higher contour to a lower contour. The partial x should be positive. But we can actually estimate. Okay, any questions about that? Good. Okay. So we have an awkward amount of time left. Oops, did I stop the share? I did. We'll talk about this image. Maybe I'll just start with this next time, but this is actually in 14.3. We basically covered 14.1 and 14.2. And so I'll post the homework today for Tuesday. That'll be on like some of that. And then 14.3, it's there's some stuff here that's important that like, maybe I'll just write this on the board just as a preview. Like we're following, if you want to estimate, or I won't write it on the board, I'll just say, if you want to estimate the height of a, like if you know what's going on at this point on a graph, right? This is height, this is the point A comma B, and this is height f of A comma B. And you want to estimate what's going on over here. We've done this, you've done this down a dimension. Like you've done this in single variable calculus where it's like the graph is curvy. So instead of following the graph, you follow the tangent line and try to estimate what's going on at that nearby point using the tangent line. There's a very similar idea here, which is the surface is curvy, so you follow the tangent plane. And if we want to try to estimate what's going on at this point, x comma y, it might be hard to compute this number, but we can compute partial derivatives and you can sort of see why. It actually just comes from the tangent plane equation. I mean, there's a nice picture here that explains this, but like, it also comes from the tangent plane equation that like, this is basically this x slope times delta x plus the y slope times delta y, and that gives you the change in z, an estimate of the change in z. Of course, these are very far apart, but if you imagine going very close, like, you know, again, zooming way in, this surface will flatten out, and you can imagine estimating changes. So like, almost like back in this picture, I mean, what we're gonna wanna talk about, I guess one thing, reason I'm bringing this up is like, we're talking about the partial x and the partial y, the slope in the x direction and the slope in the y direction. But what if I wanted to have the slope like in a different direction? What if I wanted to go in the northeast direction from this point instead? Right, we should be able to find a slope in other directions besides just positive x and positive y. Those are the easiest. Those are the easiest algebraically because we can just differentiate. But we're gonna wanna know, like, what if I wanna head off in a specific direction? What's the slope in that direction? And so you could imagine doing something similar here. I could like leave this point, go in the northeast direction, end up at this point, right? And then you could say, well, it's the change in z, which is -4 still, but now it's the change in the horizontal, which you could compute. There's actually another question like this on a homework where you had to go between two different points on a contour map and compute the delta f over delta horizontal movement, like we had to compute the distance between these 2 points, and then you had to look at the change and then take the ratio, and that's the average value. That sound familiar from the homework? No, kind of. Sorry, I don't remember the problem number, but it was like you had to go between 2 points on a contour map and estimate the change in z, estimate the distance, and then take the ratio. And so that's really, that's kind of the next big thing we're gonna wanna do once we understand tangent planes, is just like, oh, the actual, if I want a derivative in any direction, there's gonna be a nice way for us to compute, like basically leave this point in any direction. Actually, this is really why we've been doing vectors, because we wanna be able to leave a point in any direction, and we describe that by a vector. And then we wanna know the slope in that direction. It's called the directional derivative. So you shouldn't be satisfied with just the partial x and partial y. There's more directions you could go. Okay, so that's kind of just a preview of what we're gonna do, a little bit of a preview of what we're gonna do next week. So let's end a couple minutes early. How about that? It's Friday, I feel it.